Okay, so welcome to Math349 Operations of Order. This is lecture, I believe, 22. So this will be the last of the generating functions lectures. And then after this, the request was to move to talking about gaps. If you have other topics that you want me to cover, please just let me know. And so last time we started looking at the generating function of an interesting sequence, right? And we looked at the special case of multiplying your function A by another function B, matching the coefficients. And besides, I can just go back a little bit. And when we match the coefficients, we got some new function C. And so the coefficients of C come from knowing the coefficients of A and coefficients of B. And so the kth term of C was coming from all terms A times B with the sum of the indices exactly equal to K. And we noticed for these sequences we were looking at, where we were trying to count how many paths are there from 0, 0 to nn that stay on or below the diagonal, the answer had this beautiful relationship of Cn was equal to the sum of Ck minus 1, Cn minus k. And we were able to use that to get some information about the generating function. And so we got x, C of x squared equals C of x minus 1. So we need to solve that today and come up with an explicit formula for C of x. And then once we know an explicit formula for C of x, then the question is, can we deduce formulas for the individual coefficients? So when we started, we first just tried to count how many paths were there. And we saw by gathering some data, we got a nice conjecture and we were able to prove that. We could try to do the same thing here. We started gathering some data for small values of C's. It looked maybe it was Fibonacci for a while, but then when we got more data, we saw it was not Fibonacci. We could try to get more data and see if we can figure out what it is. But this is a more formal process that will give us an explicit formula. And it illustrates the powers of generating functions. All we have to do is just form the function whose coefficients are what we want to know, and hope that at the end of the day, after we do some algebra, we can get an explicit closed form expression. So we have, the equation was x, oops, I have not changed the size of the pen. X, C of x squared, I think was equal to C of x minus 1, yes. Was equal to C of x minus 1. How do we solve? How do we find C of x? So what method could you use to solve for C of x? Use the quadratic formula. Solve by quadratic formula. So let's say W equals C of x. We'll get xw squared minus w plus 1 equals 0. So w is equal to 1 plus minus the square root of 1 minus 4x, all divided by 2. So, C of x is 1 plus or minus the square root of 1 minus 4x over 2. Uh-oh, there's two possible solutions here. We have to figure out which one is correct. Now, we know that C of x is the sum and goes from 0 to infinity of Cn x to the n. Does anybody remember what C0 was? 1. What was C1? 1. What was C2? 2. C3? I think it was 5. I think it went 0, 1, 1, 2, 5. So can we use the fact that we know at least the first few terms to figure out, is it the plus sign or the minus sign? Is there any value of x where we can evaluate both the infinite sum and the expression for C of x very easily and figure out then if it's the plus sign or the minus sign? Yeah, take x equals 0. If x equals 0, then C of 0 has to equal 1. Plus sign or the minus sign? So want the plus sign. Okay. So we now have a formula for c of x. So c of x is going to be 1 plus the square root of 1 minus 4x over 2. Hopefully I have not made any mistakes. Let me see. And did we checked all this work? We haven't made a mistake anywhere. Okay, we add 0, subtracted 0, x c of x. Okay. So now, how would we get the coefficients from this formula? Yeah, I mean, we know a formula for c of x, a closed form expression. I don't care if it works well. I want to find the coefficients. So how do we find the CNs? It's okay if it's a bad way. I just want a way that would work. So we plug in 1. Unfortunately, if we plug in anything other than 0, we get every term contributes. And so we would just know there wouldn't be enough to let us, determine what the C's are. We would have infinitely many equations to solve. What was nice is when we took x equals 0, only the constant term survived. There's no value of x that only the linear term will survive. What could we do so that only the linear term survives? We've seen this before. Differentiate, and then do what? Plug in what value? 0. So note, c prime of 0 is going to just be c1. How do we calculate c2? Are you sure? So if we take 2 derivatives, we would get 2. No, it is over 2, but I don't want to say over 2. I want to say over what? It's the same as 2, but I want to write it differently. 2 factorial will be c2. What would I do for c3? It would be the third derivative divided by 3 factorial would be c3. Because if I take 3 derivatives, by terms of constant, linear, and quadratic in x, when I take 3 derivatives, they vanish. If I take a term of degree 4 or higher, if I take 3 derivatives and then set x equal to 0, they vanish. The only term that survives is the x cubed term. So x cubed, when I take 3 derivatives, gives me 6, which is, or 3 factorial. And so I just get 6 times c3 will be the third derivative. So we can find the coefficients. We just have to take the derivatives of this. Is anybody looking forward to taking the derivative of this function? Why not? Yeah. Well, I mean, this doesn't, what's so bad about this function for taking derivatives? Yeah, we have the damn square root, right? So, the question is, are there tricks we could play to try to get the derivative of the square root? We need, yes, we need to expand 1 minus 4x to the 1/2. Yeah. The 1/2 in front of it is fine. Once I go past x equals 0, that's no longer good. Once I go past the 0th term, once I start taking derivatives, the 1/2 doesn't matter. The plus or minus 1/2 in front of this is not a big deal. It's I have to expand this. So really, it's essentially asking, what is the Taylor series expansion of this? So we want to Taylor expand. Does 1 minus 4x to the 1/2, does this look structurally like anything you've seen before? It's not going to be exactly the same, but it should look like something you've seen before. Where we do know how to expand that. So much of math is about pattern recognition. What have you seen that looks a lot like 1 minus 4x to the 1/2? Yeah, it looks like 1 plus x to the p. So maybe this is, it's similar to the binomial theorem. And for that, if I gave you x plus y to the n, that was the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k, or x to the n minus k, y to the k. It doesn't really matter which way you do it. This looks very similar to the binomial theorem. The difference is we have a 1/2. So it turns out there is a generalized binomial theorem. And this was a big result from Newton, where he generalized the binomial theorem, and they define R choose k to be R times R minus 1 all the way down to R minus k plus 1 over k factorial. If R is an integer, this reduces, positive integer, this reduces to the standard notion of what's going on. We basically want to multiply by, if R is an integer, multiply by R minus k factorial over R minus k factorial. So if we have an integer, we can just multiply by R minus k factorial over R minus k factorial, and this becomes the standard binomial coefficient. The claim is this is what is true in general. And so over here, if I take a general R, I would start getting things that look look very similar to these standard expansions. R no longer has to be an integer. This is well defined. It reduces to the integer case when R is an integer. You really want to try to find things like this in mathematics whenever possible. When can you point to something you've seen before to build intuition, to generalize, to extend? So when we're looking at this, we have a conjectured formula for the expansion of x plus y to the R. Now, in a normal case, if R is an integer, let's say R is a positive integer, what's going to eventually happen in this infinite sum? Let's say R is 1701. What will eventually happen if R is 1701? What will go to infinity?
Doesn't it just become arbitrarily large?
Well, I have this expansion, x plus y to the R is x to the R plus r x to the R minus 1y plus r minus 1 over 2 factorial x to the R minus 2y squared. I have infinitely many terms. If R equals 1701, what's going to happen in this infinite sum? Better, right? I mean, if I take any value, if I take R to be 1701, I just have x plus y to the 1701. This clearly should converge. But if R is an integer, we know the binomial theorem. What should happen? Should we have infinitely many terms if R is a positive integer? No, the binomial theorem has only finitely many terms. If I give you a power of 10, how many terms are there in x plus y to the 10? Almost.
No.
I'm sorry? 11, right? How many terms are there in x plus y to the 17? How many terms are there in x plus y to the 1701? 1702. What's going to happen in this infinite sum if I take R equals 1701? What will happen as I march down? So the first term is just 1. Then I have R. Then I have R times R minus 1. R times R minus 1 times R minus 2. Then the next term I add an R minus 3. Then an R minus 4. So if you think of R as 1701, I've got 1, 1701. 1701 times 1700. 1701 times 1700 times 1699. The terms are getting larger, yes? Eventually you'll get a 0. When will you get a 0? Yeah, the 1702 term, I keep subtracting. Eventually I'm going to get R minus 1701. If R is 1701, what's 1701 minus 1701? 0. And then when I get the next term, I'm still going to have that r minus 1701. It's still going to be 0. So there's only going to be finitely many terms. So if r is a positive integer, only finitely many terms. So this will reduce to what we've seen before. So again, whenever you see something, you always want to check and see, does this reduce to what we know? The binomial theorem only has finitely many terms. If I take r equals 1701, I'm only going to have finitely many terms. This doesn't prove that Newton's generalized binomial theorem is correct, but it at least has a chance. We know what the answer is in the case when you have r as an integer, a positive integer. So whatever Newton is conjecturing or claiming, it damn well better reduce to the standard binomial theorem, and it does. And then he says, if you take 1 plus the square root of x, this is what you get. Now we had the square root of, I think, 1 minus 4x. So this is then doing x equals negative 4x. So we would get 1, and then the next term would be minus 1/2, and then we'll have a negative 4. So the minus a half, oh no, I put in the negative 4x, okay. And then the next term will be minus 1/8 4 squared x squared. And then the next one will be it would be minus 1/16 4 cubed x cubed. And the next one will be minus 5 over 128 4 to the 4th x to the 5th. No, because I've got x is negative 4x. When I square it, the minus sign is squared. And then I think we said we wanted a plus sign with this, and we wanted this over 2. I'm a little worried that I'm off by a sign, but okay, we said now we wanted, I think, 1 plus this over 2.
Oh, yeah.
And so let me double check and see if we made a mistake with the signs. I think we've somehow made a mistake with the signs. I don't want to try to fix that right now. So if we do 1 plus this over 2, we would have 1 plus this all divided by 2. Oh, wait a minute. I now know the mistake we did. We have to divide by 2x, right? The leading term was not 1, the leading term was x, right? Okay, so now if we take the plus sign, we would clearly get something that's undefined. It's got to be the minus sign. Right? This is why I always hate working with a quadratic where the leading term is not 1. Because then when you're doing the quadratic formula, you've got to remember to put in the x. We forgot the x. So we know when x equals 0, we should be getting 1. So how would you evaluate this when x equals 0? If I have the plus sign, the numerator is converging to 2, the denominator is converging to 0, it blows up. So since I only have 2 choices, if one choice doesn't work, who said whenever you eliminate the impossible, whatever remains, however improbable, must be true? Who is this? Sherlock Holmes. Whenever you eliminate the impossible, whatever remains, however improbable, must be true. If there's only 2 possibilities for C and one of them is wrong, the other one must be correct. So it has to be the minus sign. Now, if we take the minus sign, what would happen? Well, the numerator would then become 0 when x equals 0. The denominator would become 0. Oh, excellent. We get 0 over 0. How would we handle 0 over 0? L'Hopital. So then we would use L'Hopital to figure out what is the limit as x goes to 0. So if we use L'Hopital, so the limit as x goes to 0 of 1 minus the square root of 1 minus 4x over x, it's the limit as x goes to 0. The denominator is just 1. The numerator, I've got 1 minus 4x to the 1/2. So I'm going to get a 1/2, 1 minus 4x to the negative 1/2. And I've got the derivative of the inside, which will give me a negative 4x. The negative reinforces the negative sign outside. And so I get, I think, a 4. Yes? And now as x goes to 0, oh, and we had a 2x down below. And so now as x goes to 0, we get 2 over 2, which is just 1. And so this is a proof that it really is the minus sign that works. I know it had to work because the plus sign didn't work, but it's good to just check and see that. So we know that the answer has to involve the minus sign. Okay, so now we know which one it is. Okay, so now when we're going over here and we're doing the algebra, I actually want 1 minus, not 1 plus. Okay. So it's going to be 1 minus this whole quantity over 2. When I expand out, over 2x. Okay, so now when I expand out, the 1 minus 1, that's going to cancel. The minus is going to hit all the minuses and make everything positive, which is good because we're counting the number of paths, and the number of paths should be a positive number, or at least a non-negative. And so we're going to get, for the first one, it's going to be 1/2 with a 2 down below, 1/4 with a 4. So it's going to start off as x over x, which is just 1. The next term, we're going to have a 1/8 over 2 is 1/16. We have 4 squared, which is 64. I'm sorry, 4 squared is 16 over 16, which is just 1. So we get plus 1x. The next term, we're going to have 16. 4 cubed is 64. We have 2x. So that's going to give us 16 times 2 is 32, 64 in the numerator. That's going to give us a 2. The next piece, we're going to have 5 over 124 times 2 is 256. 4 times 4, I'm sorry, 4 squared is 16. Times another 4 is, and there's our 5. So is this a proof that this is the correct series expansion for the square root of 1 plus x? No, but at this point, you're beginning to be, I think, have some confidence. We've looked up to the cubic term, and we see that it's matching perfectly with what we got when we looked at these numbers. So again, we haven't proven Newton's binomial theorem yet, but by using that, we are able to match what we were calculating by hand. So if we're able to prove this, then we will have an explicit formula. Do these numbers look nice? 1, 1, 1, 5, 7, 2, 8, 16, 128, 256. Do these look nice? So one of the worst things in life is to simplify when you shouldn't. When you're trying to detect patterns in integers, it's really bad to simplify. What do the denominators look like? Powers of 2. How are we getting from one to the next? So going from 2 to 8 is a 4. 8 to a 16 is a 2. 16 to 128 is a... So the first one is 2 squared, then 2 cubed. I'm sorry, it's 2 squared to here, and then it's 2 to here, then it's 2 cubed to there, then it's 2 to there. It can be hard to detect the patterns if there's some cancellation. If I have a nice expression with a lot of cancellations, I might not be able to detect exactly what's going on. And so sometimes when you're calculating expressions, it's sometimes better not to put in the simplification and keep things fully involved. Let's try to expand out 1 plus the square root of x. So we want to expand, say f of x is 1 plus x to the 1/2. So we know we can write this, the Taylor series for f is going to be, the sum, n goes from 0 to infinity, the nth derivative at 0 divided by n factorial times x to the n. So we need to start calculating derivatives. So the first is, what does f of 0 equal? 1. So f of x is 1 plus x to the 1/2. F of 0 is equal to 1. What's f prime of x? (1/2), 1 plus x to the negative 1/2. Okay, and what's f prime of 0? 1/2. F double prime of x, what would that be? No. 1/2 times negative 1/2 times 1 plus x to the minus 3/2. I don't want to simplify things. I'm trying to detect a pattern. As soon as you start trying to simplify, you're going to make it harder to sniff out the pattern. This is why I'm spending so much time on this today, is I really want to drive home that when you're trying to figure out what the answer is, it's often better not to simplify. Now, what's f double prime of 0? Yeah. 1/2 times negative 1/2. Is it clear how I should be writing this at this point? I'm not entirely clear what's the best way to write everything. I want a few more terms. What would f triple prime of x be? We'd have 1/2, negative 1/2, negative 3/2, 1 plus x to the minus 5/2. F triple prime of 0 is going to be 1/2, negative 1/2, negative 3/2. Okay. The next derivative is 1/2, negative 1/2, negative 3/2, negative 5/2, 1 plus x to the negative 7/2. And then the fourth derivative at 0 is, I think you actually put in parentheses when you switch to Roman numerals, not sure, is 1/2, negative 1/2, negative 3/2, negative 5/2. This does look a lot like the thing we were talking about with Newton. We have 1/2, 1/2 minus 1, 1/2 minus 2, 1/2 minus 3. So if I take r equals 1/2, then we have 1/2 is just going to be r. 1/2 times negative 1/2 is r times r minus 1. 1/2, negative 1/2, negative 3/2 is r minus 1, r minus 2. It's looking a lot like that falling factorial from Newton. When I'm writing it like this. This is why I don't want to put everything together. So if I have the fourth derivative, I have negative 1, negative 3, negative 5. What do you think the fifth derivative would be? Okay. So if I gave you the nth derivative, so we have 5 terms with the fifth derivative, stopping at -9, which is just below 10. So what do you think this would be? It's going to be 1/2, -1/2, -3/2. How far do you think we go for n? So if it's n-1, then when n equals 5, we should be going to 6. Okay, so if we go to 2n-1, let's check. Yeah, there's going to be a negative sign outside. If we take n equals 5, 10 minus 1, nope. So instead of -1, what would you try? Can't be -2, that's going to be even. -3. So if we now take n equals 5, we would get 10 minus 3 is 7, good. If we take 4, 8 minus 3 is 5, good. If we take 3, 6 minus 3 is 3. So it looks like we go down to 2n-3. And so you should be able to prove this by induction. 1 plus x to the -11, oops, not a -11/2. What should it be? To the negative, I'm sorry, not n-1, 2n-1 over 2. And this, your power is 1 less than double of that, and that is 2 less than this. So you should be able to prove this by induction. And the pattern is pretty clear, and you can see that every time we take the derivative, we're going to increase the numerator of the fraction here by 2. We're going to bring down another one over here. So this looks very reasonable. Okay. So is there a nice way to represent this number? So we can write this in terms of the falling R's, right? The first one is just R, then it's R times R-1, R times R-1, R-2. That's looking a lot like Newton. But we have this extra stuff. We have this n factorial down below. So we want to play some games. We have f of n of 0 over n factorial. Now, how many terms do we have below in the denominator? When we had 3, the third derivative, how many terms were there? How many fractions were there when we had 3 derivatives? 3. When we had 5, how many terms were there? 5. So when we have n, there's going to be n terms, right? So I'm going to write the fraction in a very nice way. I have n factorial, I have n fractions, each fraction has a 2. So I can write this as 2 times 4 times 6 times 8 ... times 2n. This is coming from all the powers of 2. I have n powers of 2, and I have an n factorial. So n powers of 2 and n factorial. So 2 to the n times n factorial is 2 times 4 times 6 ... times 2n. Does everyone agree that that's the bottom? Everybody comfortable with this? I have n fractions. Each fraction has a 2. I have the numbers 1, 2, 3 all the way up to n. So just have each factor of n factorial gets a 2. And so now instead of having the numbers from 1 to n being multiplied, I have the even numbers from 2 to 2n being multiplied. So the denominator is just the powers of 2. If you look at upstairs, I've got some number of negative 1s. So how many negative 1s do I have? Well, I need to do it in terms of n. When n equals 2, how many negative 1s do I have? When n equals 3, how many do I have? When n equals 4, how many do I have? So it should be -1 to what power? When n was 2, it was to the first power. When n was 3, it was to the second power. n minus 1. So something like that. So I can figure out what the -1 is without too much trouble. And then I'm going to have 2n minus 3, 2n minus 5, dot, 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 times 3, times 1, times 1. So when we look at this, does this look like anything you've seen? So look at the numerator. Do these look like anything you've seen before? I'm sorry? Yeah, it looks very similar to the numerator for n choose k. What am I missing? Well, it's not n choose k, but it's something close to that. It's not complete, it's missing something. But what factorial does this look a lot like?
Like a external answer.
Well, what did we have? 2n minus 3, 2n minus 5, 2n minus 7, 2n minus 9. What would you like to have if you had a binomial coefficient? What should the numerator look like? It's missing the evens. And so it might have actually been a bad idea for me to simplify things like this. Let's put in the evens. So I'm going to introduce the notation m double factorial means m times m minus 2 times m minus 4 dot, 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 all the way down to either 1 or 2. Double factorial means every other. And so what we're missing here is I'm going to multiply by 2n minus 2 double factorial over 2n minus 2 double factorial. And when I do that, I'm now going to get the numerator is -1 to the n minus 1. I'll then have 2n minus 2 factorial. And down below, I'm actually going to factor things out maybe a little bit. 2 to the n times n factorial. And then 2n minus 2 is going to be 2 to the n minus 2, or maybe n minus 1. N minus 1 factorial. Is this beginning to look like a binomial coefficient? So by multiplying by 2n minus 2 double factorial over 2n minus 2 double factorial, I filled in all the evens. And so I now have 2n minus 2 all the way down to 1. And then in the bottom, I've got n factorial, and I've got an n minus 1 factorial. What binomial coefficient does this look a lot like? Is it a binomial coefficient? If I have 2n minus 2, what should these sum to down below? So if I give you n choose k, what's the denominator of n choose k? It's n factorial over what? K factorial, and what else? And what does k and n minus k sum to? N. So when I have a binomial and I'm expanding it out, the two factorials in the bottom, their numbers sum to n. So if I give you 5 choose 3, it's 5 factorial over 3 factorial, 2 factorial. 3 plus 2 is 5. I have a 2n minus 2. I have an n and an n minus 1. What do n and n minus 1 sum to? They sum to, what does n and n minus 1 sum to? 2n minus 1. I want a 2n minus 2. Is this sum good, or is it a little bit off? Off by 1. So let's pull out an n. So this will be negative 1 to the n. I'm going to have a 2 to the 2n minus 1. I'll have an n. And I'll have 2n minus 2, choose n minus 1. So if I write n factorial as n times n minus 1 factorial, I can now take the n minus 1 factorial, the n minus 1 factorial, and the 2n minus 2, and give myself a 2n minus 2, choose n minus 1. And so it looks like this is now a binomial coefficient with a factor of 1 over 2 to the n minus 1 and an n. Now what we do is we take this and we go back into what we had before. What did we have to expand out? We had 1 plus or minus the square root of 1 minus 4x over 2x. Right? Oops. So we have cx was 1 minus the square root of 1 minus 4x over 2x. Okay, and we know that the expansion of 1 plus x to the 1/2, this looks like it's the sum, n goes from 0 to infinity of negative 1 to the, did we say to the n? And n minus 1. And then we had, was it 2 to the 2n minus 1 times n times 2n minus 2, choose n minus 1. Okay, so that looks like that's what we had. So now we have 1 plus 4x, I'm sorry, 1 minus 4x, 1/2. So now, oh, and of course, there's an x to the n here. If n is even, does it change the sign of the term? No. If n is odd, does it change the sign? If we're replacing x with negative 4x, whenever n was even, the x to the n and negative 4x to the n, they both have the same sign because it's n is an even power. But if n is odd, it changes the sign. So when n was odd, was the sign positive or negative? So when n was a positive even number, what was the sign? Negative. So now the signs are always going to be positive. Wait, if n is odd, the sign was positive. So now the sign becomes negative. And if n was even, the sign was negative. So the signs are always going to be negative now. So it's going to be negative, and then we'll have a sum, n goes from 0 to infinity, of 1 over 2 to the 2n. And then we have 1 over n, 2n minus 2, choose 2. And then x to the n is going to give us a 4 to the n, x to the n. Well, what can you say about 4 to the n divided by 2 to the 2n? So what's 4 to the n divided by 2 to the 2n? One. 2 to the 2n is just 4 to the n. So this is the same as the sum, n goes from 0 to infinity, of 1 over n, 2n minus 2, choose, this should be choose n minus 1, choose n minus 1, x to the n. And we've got a negative sign outside of all of this. So now if we look at 1 minus the square root of 1 minus 4x over x, I know that the constant term is going to just be 1. Oh, no, I'm sorry, we have a 2x over here. Sorry, we have a 2x, right? So I know the constant term is just 1. We've talked about this before. And then I'm going to have a sum. The minus sign is going to cancel that minus sign. And now n is going to go from, when n was 0, that canceled with the 1. Okay. So I think I'm going to just start off with n equals 1 to infinity of 1 over n, 2n minus 2 over n minus, choose n minus 1. And we have an x to the n. We're dividing by 2x, so it becomes x to the n minus 1. And I think it's just going to be like this. So the n equals 0 term canceled with the 1, and this is what is left over. Okay. And this is supposed to be equal to the sum, n goes from 0 to infinity, of Cn x to the n. So everything seems to be shifted a little bit. So let's over here, let's let m equal n minus 1. Okay? So if n goes from 1 to infinity, what does m go from? 0 to infinity. And so then this sum would become the sum, m goes from 0 to infinity, 1 over, now if m is equal to n minus 1, what does n equal? It's m plus 1. So this is going to be 1 over 2 m plus 1, 2n minus 2, that's just the same as 2m. n minus 1 is the same as m. X to the n minus 1 is just x to the m. And that's just the same as the sum, n goes from 0 to infinity, of Cn x to the n. So Cn would just be 1 over 2m plus 2, 2m choose m. And we have an explicit formula when all the dust settles for the nth number of this sequence. So there are a lot of places where the algebra can be done incorrectly. I've shown you at least 1 or 2, not on purpose, where the algebra was done incorrectly, but we were able to recover before class ended and get an explicit formula. This is the number of paths from 0, 0 to nn that stay either at or below the main diagonal. The answer is beautiful. The answer is also reasonable. How many total paths were there from the bottom left to the top right? 2m, 2 is m. Oh, I've switched to m's and n's are all. It's easier to just change that one than all the others. So we know that there's at most 2m, 2m paths. Good. This is telling us that the answer is less than that. That's reasonable. It's also telling us that it's actually of a similar order of magnitude. Yes, in the limit, it's going to be much, much smaller, but 2m, 2m goes so much faster than m does that we're not really losing that much. Does this look like this is going to be an integer? It's not clear immediately that that binomial coefficient is going to be divisible by 2m plus 2. Right? So there's definitely some work that needs to be done to show that everything is going to work out. It is possible that I might have made a small mistake somewhere. I wouldn't be surprised if that happened. I I was actually thinking that there should have been an extra factor. Oh, wait, there's an extra factor of 2 somewhere. We're supposed to divide by 2x. Did I drop that 2? We had a 2n minus 1 to the n. So over here, when we had 2n minus 1, I might have dropped the minus 1 over here. So this is where it's always possible to make very small mistakes. That would give us an extra factor of 2 up here, but then we have the 2 down there, which cancels that. Okay, good. And so there's no factor of 2 here. Good. You know how I was able to quickly tell that I had made a small mistake? If 2m plus 2 is prime, that can't divide this number. So I know there has to be a mistake. And so we had dropped an extra factor of 2. These are called the Catalan numbers. I'll say a little bit more about that. Have a great weekend. Okay. They're called the Catalan numbers.